Welcome, students. Today we embark on a journey into the deep structure of physical laws, moving beyond the familiar territory of Newtonian mechanics. For over a century, Isaac Newton's Principia was the absolute authority. His second law, F equals ma, taught us how to predict motion by summing up every force. But in the late 1700s and 1800s, Lagrange and Hamilton developed entirely new approaches. These aren't just formulas, they are profound new ways to see the universe. These frameworks are essential for modern physics, forming the foundation for everything from quantum field theory to general relativity. To understand these concepts, we'll use a classic example, the simple pendulum. A mass m hanging from a lightweight massless rod of length L pivoted at the other end. We can specify its position in two ways, either by the arc length s traced by the particle, or more elegantly, by the angle theta it makes with the vertical. They're related by theta or SL. Let's first briefly review how to understand the pendulum using Newtonian mechanics. We start by drawing a free body diagram to keep track of all the forces acting on the particle. There are only two forces, gravity mg pulling straight down and tension T pulling inward along the rod. Then Newton tells us to add up all the forces and write the equation of motion. But what we're really interested in here is the tangential component, that is, the component of the force and acceleration along the circle where the particle is constrained to move. The tension doesn't contribute anything here, that's pointing radially toward the center of the circle. So the relevant force is the tangential component of gravity, which you can see is mg sin theta. Then the F powered h times a equation for S reads mass times acceleration S double dot equals negative mg sin theta. Plugging in S hr L theta, we can write theta double dot equals negative g over L sin theta. This is the equation of motion for theta. It's a differential equation that governs the motion of the pendulum. And it's actually pretty complicated. Too complicated to write down a simple expression for the solution in general. Now let's look at the Lagrangian formalism. Newton told us to start by writing down the total force. Lagrange tells us to start by writing down the kinetic energy K and potential energy U, and then to take their difference. L add K U. L is called the Lagrangian. It is not the total energy K plus U because of that pesky minus sign. Let's see what the Lagrangian is for our pendulum. The kinetic energy is just 1,2m v squared. In terms of theta dot, this becomes 1,2m L squared theta dot squared. Potential energy U comes from gravitational potential, which is just mgy where y is the height. If we put the ground level at the height of the pivot, then v sine L cos theta. So the potential energy is U id mgl cos theta. Then the Lagrangian for the pendulum is L main 1,2m L squared theta dot squared plus mgl cos theta. Newton told us to write F sectus ma. Lagrange instructs us to compute the Lagrangian L, and then write down the Euler-Lagrange equation, d dt, partial L, partial theta dot, in partial L, partial theta. The curly dels stand for partial derivatives. Don't worry, for practical purposes, they behave like regular derivatives. The Euler-Lagrange equation is the condition for the action S, which is the integral of the Lagrangian, to be minimized. The claim is that of all the paths a particle could choose, the one it actually chooses is the path that minimizes the action. This is the principle of least action. This remarkably gives us the same equation of motion for theta without having to deal with force vectors. The Lagrangian is a very useful way of quickly getting at the equations of motion for a system. We can just choose whatever coordinates we like to describe our system. It also makes it much easier to deal with constraints and to understand symmetries. Finally, let's look at the pendulum with Hamiltonian mechanics. Instead of Ku, this time let's write down the total energy E as K plus U. Remembering that the momentum is P arc bis ml squared theta dot, we can rewrite this as the Hamiltonian H. H du P squared over 2ml squared minus mgl cos theta. H is the starting point for Hamiltonian mechanics. More generally, it's defined by the Legendre transformation. We use Hamilton's equations to write down the dynamics. Hamilton gives us a pair of first-order equations for theta and p. Let's see what we get. Theta dot, partial h, partial p, and p dot, partial h, partial theta. So Hamilton's equations for the pendulum are theta dot, stacked p and ml squared, and p dot, stacked mgl sin theta. The first equation is just the definition of momentum. If we combine them, we get ml squared theta double dot equals negative mgl sin theta, which is once again the original equation of motion. So Hamilton's equations are equivalent to F Shaz ma. But what does that buy us? Hamilton's equations gain us a new geometric perspective on mechanics. As the pendulum moves, we trace out a curve in the theta p plane known as a flow on phase space. To specify what the pendulum is doing at any given instant, we just need to give its position and velocity. With this initial data, we can figure out what the pendulum is doing at any later time. The theta p plane is called the phase space of the system, and the curve is called a flow. These flows are very special. They won't travel along any old curve in the phase space. In particular, because the energy of the pendulum is conserved, h is a constant of the flow. That means that whatever the initial energy h0 of our starting point was, the flow will be trapped on the curve in the phase space where the energy is h0. Notice that there are two qualitatively different types of constant energy curves here: the closed loops near the middle and the wavy lines at the top and bottom. They're separated by the pointy football-shaped curve in between called the separatrix. If you found this interesting, I invite you to buy my book, The Engineering of Life, where we discuss quantum laws, thermodynamics, and the field in general. Buy the book on Amazon when it is launched pretty soon and leave a review if you would. Understanding Lagrangian and Hamiltonian mechanics is your first real step into the deep structure of the universe. Thank you for joining me today. Keep exploring and keep questioning. Goodbye for now.